Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. So now the sound is working in the lecture hall. I hope on Zoom too. Before we start, or at least continue in the data modeling section, I would like to ask you a question to check that you've been following. Here you go. You should know that, right? So HBase can run on top of HDFS. However, I explained that HDFS is throughput bound, so it's the latency might not be very low, and yet, in spite of this, HBase is fast. How can it be? Answer one: HBase is not actually faster; it has a high latency, just like HDFS. Answer number two: because HBase has key values in the mem store as well as caches. Or answer number three, because it short circuits data nodes. Or answer number four, because it uses smaller HDFS block sizes of 64 kilobytes. (42). Stop here. Let's look at the intermediate results. We have two very popular answers, and both are in fact correct. The first thing is that there is this batch processing way of writing the data. You don't write it to HDFS every time. Instead, you accumulate in memory, and when it's full, when the mem store is full, you flush. So this is one way. And there's also caches, meaning that some of the values that are in HDFS are also in memory if they're used often. There's also indices inside the H files. And short-circuiting data nodes, yes, absolutely. This is one of the reasons why it's faster as well. Because since I told you that the client of HDFS by default writes the first replica of every block to the same machine where it is, and now we know that the region server is a client of HDFS. So the region server is writing the first replica of all of the blocks, all of the HDFS blocks of the H files for these regions that it's responsible for on the same machine. That was a long sentence. Okay, so now I'm going to switch back to the slides and we'll continue. All right. So first, do we have any questions on what we did yesterday? Anything that is pending that you're wondering? Okay, so I'll assume you can ask on you will ask on the Moodle forum if there is anything, and of course the exercises should help a little bit. So where were we? So we discussed data modeling. The most important lesson of yesterday is that syntax is in fact only a physical layer. When you store data as JSON or XML, that's just the text you use in the file when you put it on HDFS or S3 or HBase. But in fact, when you want to process JSON or XML, the first thing you do is you parse it into an in-memory representation based on trees. And in fact, everything else will be done on that memory representation, not directly on the JSON or XML text. So that was the most important one. And serialization is the opposite. When you take the memory representation and write it back to JSON or XML. And then we saw that one of the things you can do once it's all loaded into memory is validate it. So we saw that you can define constraints or some expected structure on your data in XML and JSON. And then you can answer a second question. After well-formedness, you can also answer a validation question. Is my well-formed XML or JSON document valid? Okay, so this is what we discussed last time. And then we saw that you can validate typically millions of objects or XML documents at the same time that are stored somewhere. And then you can enforce that any future documents that get added to the collection will also be valid against the schema. Then we saw that when you do that, and if your schema has enough constraints, your collection becomes homogeneous because all of the documents there will have the same structure. And we will see and discuss that in that case, you can make the processing much more efficient because you can compress the way it looks like in memory. You can take less space, and you can even write it back to files in a binary format that also take less space. So that's the benefit of having valid data. Now, there are many different validation technologies out there. There's not just one. So there are several ones for JSON. There's also several ones for XML, and there's actually many others that even go beyond JSON and XML. So it looks daunting, right? All these technologies, how can you learn them and so on? Is it challenging? Is it complicated? Well, I have good news for you. And the good news is that the type systems of all these technologies, they pretty much look the same. So if you learn a few of them, we'll look into 3 of them. In fact, it's as if you've learned them all because the principles are the same. So after learning these, the ones that I'm going to show you, you can learn any other technology in just a few minutes because then you can just look at the documentation, see how it maps, and very quickly you will be able to use it, right? So I really intend this lecture to be generic. And so because of that, what I'm going to show you here, the type system is technically agnostic of the technology. It's generic and common to almost all of them. Maybe I'm too far away. Or it's on strike. There you go. So the first trait that they all have in common is the distinction between 2 kinds of types. The types are basically what you validate your data against, right? It must be like something must be an integer, something must be an object with these and these keys, like a class in Java. And there's 2 kinds of types, the atomic types and the structured types. Now, is it really a surprise to you? I think not, right? We've seen that before. We've seen that first when I talked about the first normal form, that in the first normal form, you want all of the types to be atomic and nothing nested. So the nested stuff would be structured. We also saw it when we looked at JSON. When we looked at JSON, I told you there are 6 building blocks. 4 of them are atomic and 2 of them are structured, right? Atomic is string number, Boolean null, and structured is object and array. So you see it's true in JSON, it's also true in XML, so you can distinguish between atomic types and structured types. And that is true of, I cannot think of any technology that doesn't, basically. So there's always this clean separation. You can think of the atomic types as the leaves in the tree representation and the structured types as the intermediate nodes, the non-terminals, you would call them in the grammar, that are not the leaves. Okay, who has an intuition of that? Okay, very good. Now I'm going to go through the restaurant menu. I love restaurant menus. So the restaurant menus of the atomic types in a generic way, because what I'm going to show you, the kinds of types you have, they might not have the same name, but they are still the same everywhere. So the first, I'm going to go quickly because you're computer scientists, most of you, so I think that you know sufficiently programming to not really be surprised by what's going to come. So the first type that is absolutely everywhere is strings, right? So the strings are technically sequences of characters. Technically, when they're in memory, they're already in Unicode code points, right? UTF-8 and the such would only be an encoding. But then when you load them in memory, you can have more efficient representations. So there's just sequences of characters. Now, if you want to sound fancy in front of your mathematics friends, you could say that strings, maybe you heard it in theoretische Informatik, they basically form a monoid structure. You can concatenate strings, the empty string is the neutral element, and so on and so on. So, all right. So these are the strings. This is one of the type, the most generic one. Don't know what's going on. Maybe it's the battery, but normally it's supposed to vibrate when there's no more battery. So at least it works here. All right. So the next kind of types is numbers. Now, numbers is a zoo by itself. There are so many different types of numbers that I'm going to just give you the general classification of the sort of types you can have from a database perspective. So first, you have the types that correspond to a physical limitation of on the storage. But on the logical level, it just means you have an interval. That's what it really means logically. So for example, you can have 8-bit numbers. What that really means is that it's the numbers between 0 and 255, or the number between minus 128 and plus 127, depending if you want it signed or unsigned. But basically, it's an interval. Then you have the same with 16 bits. With 32 bits, that brings you all the way to 4 billion, or between minus 2 billion and plus 2 billion. And this one was broken on YouTube with Gangnam Style. It actually brought back the counter to negative. So this is why YouTube switched it to 64 bits. And in 64 bits, that goes all the way to 16 quintillions. I don't think anybody is going to make a YouTube video with 16 quintillion views anytime soon. So that should suffice. So 64-bit now is the common standard today for many things. Okay, so these are the ones that correspond to integer intervals, and physically they are very efficient because they have a fixed number of bits. Then you have something that we love in databases. It's a bit less common in older languages like C or Java that typically restrict the precision. But basically in databases, you like to have arbitrary precision decimals. So first, you can have the decimals where you say, okay, I have that many digits in total of precision, among which that many digits after the decimal period. So basically, this is called fixed point decimals, because the point is always here. You basically store all the bits corresponding to all these digits, but you always put the point at the same place in these digits. So this is also a possible way to store the numbers, and so there are types for this. But most importantly, you have types that give you arbitrary precision and scale. It means that it's basically any integer without any constraint, any decimal number without any constraint. Remember that a decimal number just means any real number that you can write in base 10 with a finite number of digits. This is what it means, a decimal number. So it's just a sequence of digits with a dot in the middle. And so in database systems, especially with XML and JSON, you can have that. You can have this theoretically unbounded type for such numbers. Then you have the double and float that you have in many languages. So it's a standard that's called IEEE 754. I have no idea why I know that by heart. IEEE 754. And that any CPU can process it very efficiently. It's basically about putting the number in scientific notation, right? It has a mantissa times 10 to the power of something, or times 2 to the power of something, depending on the one you use. And basically, you store in the 32 bits or 64 bits the sign on 1 bit, then you have the power of 10 or 2, and then you have the mantissa that is right there, right? And so basically that would be called float in many languages, gives you 7 digits of precision, and this one is called double in many languages, give you 15 digits of precision. That also exists in XML and JSON. Do not be confused, in Python they call float the one on the right. So it's the same as double in other languages. Okay, then we have Booleans. I think I'm going to stop right here. You know what a Boolean is, true, false. There's only these 2 values, right? There can just be multiple literals. I'll come back to the literals, but it's still true and false. Then we have dates and times. Dates and times are actually super important as soon as you have customers, because they need dates and they need times. And sadly, they are often neglected by software developers. Like when you invent a new system, the dates and times are the last thing you are going to think about, even though it's actually very important. That's the reason why it's often added as an afterthought. Like in Java, for example, you had multiple versions of external libraries until it was finally taken over, I think, in Java 8. So dates are very important. So there's many calendars, of course. So here I'm showing the Gregorian calendar, where you have a year, you have a month, and you have a day. Then you have the times, where you have the hours, the minutes, and the seconds, and you can even go all the way typically to milliseconds or microseconds. I'm off by 5 minutes. Tried to target, but not exactly. And then you have the combination of both. That is called also a timestamp, where you have the exact year, month, day, hours, minutes, seconds, all the way to milliseconds. Now, what I'm showing to you is the logical value of it, right? That's how a human would interpret it. But as you might know, when it's in the computer, a timestamp is just stored as an integer. That's the number of milliseconds since January 1st, 1970, right? But that's just an efficient internal representation. A human being would think of it in this way. All right, so that's a timestamp. Then we have durations, I think is coming next. Time intervals, yes. So time intervals basically are durations. It's the difference between 2 times or 2 dates or 2 timestamps, if you want. So what I want to warn you about here, you can express them in years, months, days, hours, and so on. What you need to be careful about is this very scary wall here between the months and the days. Because as soon as you say something like 4 months and 3 days, and I ask you how many days is that, well, it depends. Is it February? Is it March? You know, it depends on the number of days in a month. So this is why I put this vertical bar here. It's not necessarily going to be forbidden to give a duration like this, but you need to be careful because then it's ambiguous. So ideally, you should try to not cross that limit. Either you talk about years and months, or you talk about days, hours, minutes, and seconds. Okay? Who is with me? All right. I'm showing to you, of course, the human representation of that. That's how we humans think of it. I will show you later sort of the ways it appears in XML or JSON. Then we have binary types. Binary types are basically just sequences of bytes. That's it. It's just like we discussed in S3 or HDFS, what objects are. It's just sequences of bytes. Can be pictures, videos, anything, just a sequence of bytes. Again, that's the logical representation as a sequence of so here I even put you bits, right? Bytes are just 8 bits, but there's also alternate representation. Who heard of base 64, for example? So this is one way to represent them as text, and there's also a hexadecimal in base 16. You can do it as well. But once you put it in memory, you just have zeros and ones, once you parse it from base 64, for example. And finally, the last one, really have to walk a lot today. Null, yes, the least interesting one. So null in JSON and XML is kind of considered in a special way. In SQL, you could say, okay, null is just the absence of value or something. But in XML and JSON, there's a distinction between the absence of value and the value null, right, in many systems. Not all of them, but many systems. So basically, you can consider that there is a type, null, that has only one value that is null, right? This is one way to think about it. All right, so these are the most used families of atomic types. You can look at any schema technology, it will more or less have this. It might have more exotic types and so on, but this is more or less it, right? Now, the next thing I want to tell you about atomic types is putting it back in context. What are we doing? We try to validate data. We use these types to validate data. We want to say, I expect this value in that object with that key to be an integer, or I expect this element to contain a date in XML, for example. But the thing is, JSON and XML, these are text files. So when you look at them, it's just a text, right? And if you remember the JSON syntax, there is no such thing as a date or a binary or anything like that. We just have strings, numbers, booleans, and nulls, right? That's all there is. So how can we possibly expect to find the date in JSON or to find the date in XML, right? Well, this is with the superpower of literals or lexical values. The idea is that the types or the type systems are a mathematical abstraction. For example, date, the date type has the set of all possible dates, right? The integer type has the set of all possible integers. But we are talking, when we say that, about the value space. When you talk about integers and you consider 2 and 42 and all these numbers, you mean it mathematically. This is the mathematical concept of 2. This is the mathematical concept of 42. When you say 23rd of October, 2024, it's the mathematical, logical concept of October 23rd, 2024, right? But the thing is, when you put it or store it in text, you will in fact put what is called a literal or a lexical value. It is basically a string. It is a string, but a string that can be decoded back to the actual value or encoded back. And again, you can say you parse and you serialize when you can use these same words, right? So for example, all of these are lexical values that all are associated with the concept of 4, the number 4. That's just 4. This is the scientific notation. That's allowed in JSON too, except the plus. Some of you asked about it. Some accept the plus, some don't. And then this is in base 2, right? The B says base 2. In some languages, you can add a B to basically say this is a base 2 literal. And this also parses to 4. For whom is that clear? So we call it a literal or we call it a lexical value, these things. And here we call it the typed value. And obviously, this is what you have in the JSON or XML when you read it fresh from HDFS or S3. But as soon as you validate and use your schema, then you basically think of it that way when you look at the data. And then in the memory, you're going to have some representation of the validated typed value that doesn't need to be the literal anymore. You might even have forgotten about the literal and just hold this in your memory. This is another example with dates. It turns out that there is also a standard for the lexical values or literal for dates. This one is called, I think, ISO 8601. That's the date specification. And it basically says 4 digits for the year, or depending if it might be before thousands, then less. Then you have a dash, 2 digits for the month, a dash, 2 digits for the day. If you ever have projects and you need to encode dates, do not make up your own format. Try to take the standard, this standard right here. It's a mistake that many people make. They just invent some representation of dates and so on. Then it is a nightmare to make it interoperable with other libraries and other tools and to parse it back. If you do it that way, this is a standard. Right? So you have many tools that are going to be able to read it, especially XML schema, JSON schema, and so on. All right, so this is for dates. We have the same for timestamps. So here you basically, it's also a standard. That's the same ISO 8601. So you have the T in the middle and still the dashes for the month, the colons right here, and then a time zone. Z is basically the GMT. And you can also put the explicit like +2 hours, -7 hours, like this kind of things. All right, so that would be the lexical value, one of the lexical values associated with this date. And then, of course, inside the memory, then you can just put the number of milliseconds since January 1st, 1970, right? But in JSON or XML, you would just have this literal. Then you have durations, which also have a standard. And the standard basically has a capital P, an uppercase P, then 1 year, 2 months, the same T as between dates and times, 3 hours. So here, that's a breach, of course, of that scary wall that I told you about, but I just wanted you to see how it looks like. This is also a standard to basically encode the durations in that way, and then you can parse them in memory to this logical value. Who is with me? All right, so this is true for every atomic type, has 3 things. It has a value space with all the logical values, a set of logical values. It has a lexical space, which is the set of all literal representations, all of the strings that can represent one of the typed values. And the third one is a mapping between the two. It's a function, or a mapping might not be injective, it might not even be surjective. No, it should be surjective, just not injective. But basically, you can map back and forth. Any literal can be mapped to the value space, and then you can map it back But technically, when you map it back, you could have ambiguities. You can have several ways of writing a literal. Then you have what's called the canonical literal value. That is the default one. That is the preferred representation when you serialize it back. Okay, so value space, lexical space, and a mapping between the two. This is what you need when you define an atomic type. Something also interesting in many systems is the notion of supertype and subtype. Now, if you do it cleanly, and unfortunately not everybody does it cleanly, normally when you have a subtype, it means that the value space is a subset of the value space of the supertype, normally, right? So this is what it's supposed to be. If you go into object-oriented programming, that might not be exactly true, or in some cases it can be a bit broken, but normally on the very high level, this is the idea. You have a subtype if the value space is a subset of the value space of the supertype. Okay, so that's the atomic types. Then we have the structured types. This is actually easier because typically there are only two of them. From an abstract perspective, it's basically lists and maps. They might be called differently, but it's lists and maps. Now in JSON, lists are arrays and maps are objects. But this is the idea. So you also find some maps in XML, as somebody correctly said yesterday, that the set of XML attributes in one element can be seen as a map. We'll see there are also structs in data frames, if you know a bit of pandas or you've seen data frames before. And lists, they correspond to JSON array, also to elements. An element, basically the children of an element is an ordered list of children that can be text or other elements. So this is why we would say it's technically a list. And also when you look at data frames, that corresponds to the array. So basically think of it as lists and maps. These are the main two structured types that you can have in most systems. Now, these are the most generic ones, but many systems allow you to define your user-defined types by basically saying, I want specifically a map that has 3 keys and each key is mapped to a value of that type. Then you define your own user-defined map, right? And then you can even give it a name and so on. But basically, the structures can either be maps or lists. You might have more than that. In some systems, you also have sets. So you do have validation engines that allow you to have sets, and so you might have a bit more. But lists and maps are really the ones that you need to have almost everywhere. Then we have the concept of cardinality that is also present in many systems. What do I mean here? I mean, in JSON, for example, the cardinality of an array. 1 element, 0 elements, any number of elements, at least 1 element, you can specify that. In XML, that would be the cardinality when you define an element and the children it can have. You can basically say that can have 0 or more child elements with that name, or it can have 1 or more child elements with that name, or it can have 0 or 1 child elements with that name, or it can have exactly 1 child element with that name. So these are the 4, right? So 1, 0 or more, 0 or 1, 1 or more. Who knows regular expressions? Great news, you don't have anything to learn. So this is the star for 0 or more. This is the question mark for 0 or 1. This is the plus for 1 or more. So it's used, we'll see in JSONic, xquery later. These are the symbols that you use to denote these ones. Some instead use adjectives. So I'm thinking of protocol buffers by Google. They say required when it's exactly 1, repeated when it's 0 or more, optional when it's 0 or 1. But you see, it doesn't really matter what it's called. There's really fundamentally these 4 main cardinalities that you can have. Who is with me? All right. So again, that's agnostic of the technology. It's fully generic, what I'm telling you here. Now, this is a slide, don't be scared. It's a slide that I created a few years ago because my students were asking for it. Because I kept saying, there's this generic way of looking at types, but then there's a lot of different type systems. And so I was asked, can you have a correspondence table between all the names of the types across multiple systems? And I said, okay, I'm going to do that, right? So this is what you get. So let me explain. So Python, you know, right? So you have a few Python types on the right. PostgreSQL, you might know. That's a relational database. These would be the SQL types that you have for your schema. Sparse SQL, we'll see it in a few weeks, so that you can wait. But basically, these are the data frame types that you can have in Sparse SQL. JSON schema, XML schema, that's what we are going to look at now and next week. And JSONic, you can see it's actually the same ones pretty much as JSON schema and XML schema. And JSound, which is I would call it a pedagogical schema language to teach. So basically, you can see here that the restaurant menu is more or less the same, but the one thing that varies is the names, right? They all mean the same here, but they are called differently depending on the system. How do you know? When you just look up the documentation and you see how every system is calling it. And again, you have sometimes things that are a bit unusual. Like I told you, float in Python actually means double in many other systems. What is interesting too is the handling of int. For example, int in Python is unlimited, and that would be called integer in JSON schema or XML schema. But int is the 32 representation in XML schema, the 32 bits, just like Java or many other languages. All right. I know you will not know that by heart, but what I want to show you is really that there is this general idea that the types are more or less the same. Some might be missing here and there, and the names might be different, but in the end, you know, they're all the same. This is really the idea here. So that should scare you less normally that you know that, because now I could, after the course, I could throw at you plenty of other schema technologies. You will notice you could fill that table with one more column, and you will be able to map also the types to these ones. Okay. So this is the end of the generic type system that is common to all the technologies. And now I'm going to go into the details of three of them: JSound, JSON schema, and XML schema. So let's start with JSound. So JSound was actually, it's not something that is really used. I designed it with a few colleagues, having teaching and simplicity in mind. The goal is really to give you the intuition of schemas, because this has a syntax that is very close to it. Then we look at JSON schema. This one is used a lot in practice, and XML schema, which is also used a lot, also by governments. All right, so JSound. So the idea on every screen that I'm going to show you, I'm going to have the actual JSON or XML right here on the upper side. And I'm going to have the schema that basically give me the constraints below. Now a bit of terminology. So this is called a schema. This one is called an instance, right? So when you have a JSON document or an XML document that you have validated against the schema, or that you want to validate against the schema, this is called an instance. Just in the same way that in Java, you would have the notion of class and the notion of object, and you would say that an object is an instance of the class, right? You can have many different objects that are instances of the same class, just like you can have many different JSON objects that are instances of the same schema. So I call the file file.json. You can actually also do it in reality, I mean, with JSON schema. And then the schema file is schema.json. But now you should notice something. You should have noticed that the schema at the bottom is also JSON. It's not something that we should take for granted, right? Could have been something else. In fact, if you take protocol buffers, for example, this is a different kind of syntax. In fact, this is going to be true of JSON schema too, and also XML schema. An XML schema is also an XML file. So this is the first thing. It looks just like JSON, even though it's a schema. So if I look at that schema, what does it tell me? Well, it tells me that I want to validate objects, and if they have a key called last, I want it to be a string, right? This string that you see here, you need to take it from the restaurant menu. So you need to take it from, in that list right here. You notice it's the same list as here. That's exactly the same names. But basically, you take it from the restaurant menu and you say, okay, last should be a string. And then you look at the instance, you say, okay, I'm trying to validate it as a string. The answer is yes, I have a string there, right? If it had been an object or an array, that would have been refused, right? That would have been rejected because an array or an object is not a string. Now, if it had been an integer or a Boolean or null, that would have been okay too, because what it does is that it forces it into a string. So if you had the number 42 without any quotes in JSON, that would just create in the memory a string with the characters 4 and 2, right? So you would force it into a string. All right? Who is with me? All right, so this is the schema. Now, if I give you other examples, before I do that, you can go to that page, even now, if you want, on your laptops. This is a sandbox, and you can actually play with it. So even the example I'm giving to you, you can basically go to that page. You can put an instance on the left and an instance on the right and a schema on the left, and you can play with that. It's called the JSound compact that you need to select. This here is running on AWS. It's actually between 4 and 8 machines. It automatically scales depending on the number of people connecting. Very small machines, 1 gigabyte or 2 gigabytes of memory, just one core. So do not expect much from them if you all connect at the same time. But it's just for convenience, something we have in the cloud that everybody can use. They restart every 24 hours. So if they crash, you just need to wait a bit. It will restart at some point. This is in fact the same server that runs in the Docker that you have. So if you're using the Docker, you can also say localhost 9090 and do the same thing with your own Docker. All right, so having said that, here's another example where I'm saying that I expect the key called last to be associated with a string and the key called first to be associated with a string. And so I can say that the instance on the top is valid against my schema, right? Now, by default, when I say that, it's optional. So I'm basically saying if first is there, then it must be a string, but it's okay if it's not there, right? So it's optional. So this is fine too. This is also valid against that schema. First is just absent. If you want to require fields, you just add a little exclamation mark here, and that basically says it's required. So now this requires the two. So here it's valid. But if you would be missing one of these, that would not be valid. That would be rejected, right? So in the compact syntax, for convenience, you can just put an exclamation mark. Then you can specify numbers, but again, I told you can put anything from the menu, right? So here, if you just use integer, it's just taking the value here. JSound looks at the lexical value. So it just takes any atomic that is in there. It doesn't care if it's inside quotes or not inside quotes or whatever. It just looks, is this the lexical value of some integer? It says 142, yes, that's the lexical value of an integer. And then it says, yes, that's valid. And then in memory, it might use an integer representation. That's an example with Boolean, where here too, it looks, is it a lexical value of a Boolean? Yes, TRUE, that's fine, that's a Boolean. Right? It would have been fine if it were quoted as well. It's only interested in the lexical value. Null here would be also valid because I told you null is a type that has only one value in its value space. That's the value null with the lexical value NULL. Now, do we have a question? Yeah.
Can we also parse a number that is quoted to be an integer?
Yes, absolutely.
Then why do we use quotes?
Oh, so the quotes are basically in the JSON syntax. If you just look at the JSON syntax, it's basically, I would call it a primitive type system, right? It just has these 4 types, string, number, Boolean, and null. Now, in XML, it's even more primitive because you just have text. That's all you have. Now, the reason why we don't care about the quotes is that what we are doing here is adding a layer on top of the syntax. It's even a layer on top of the in-memory representation. And so when you introduce the notion of a schema validation, you do not want to restrict you to just 4 types, string, number, Boolean, and null. You want all these types here. I'm showing you the full list here. All of these, that's a huge list. All of these have a typed value space. They have a lexical value space and a mapping between the two. So basically now, you can have anything that is a literal of any of these types in JSON, usually between quotes, because the only reason you would omit the quotes is if it's a number or true, false, null. But basically, from a design perspective, it's cleaner to just say, we just look at the lexical value independently of the quotes, and we ask the question, is the lexical value that I see in JSON in the literal space, the lexical value space of the type that I'm expecting? So this is the reason. It's cleaner. You could have imagined a design where you actually make a difference and you say, okay, I want my integer to be unquoted, or I want, but the problem is that, let me give you an example if you want to enforce standards. In JSON, strictly speaking, if I'm correct, you're not allowed to have a plus in front of your number. It's accepted by some engines that are lenient, but normally you're not supposed to have it. In the standard here that I'm following, it's a W3C standard, all of these types, you allow for a plus. Now, if you want to validate JSON according to that standard, then you need a way for users to be able to add a plus. But if they want to be able to add a plus in front of the number in a way that any engine will accept it, you should quote it, right? To be sure that it's going to parse. Once it's parsed in memory, you look at the lexical value and you just parse it, right?
And in some sense, this means that the validation would expect not well-formed JSON files as well.
It will expect, sorry?
Not well-formed JSON files as well. So like, for example, if I don't quote a string, this would still look at it as a string.
So it will only, so this is working on the memory, on the in-memory representation, the schema validation. Let me give you an example. Imagine that you want a date. So you put then the literal of a date in your JSON, but you need the quotes around it. Because if you don't have the quotes, that would be not well formed at the JSON level. So here you always need the quotes in there. And then you look at the lexical value, and if you validate it as a date, for example, then that will succeed and give you a date. But you never break well-formedness, right? Syntactically, it's always going to be well-formed. And the steps are really in that order. You take the text, the document, you check for well-formedness. If it's well-formed, you parse it and build the tree representation in memory. And then you work on the tree. So at that point, you're no longer in the syntax, right? Does it make sense?
Thank you.
Okay. All right. So this is the whole list of types. There's a lot of them, of course, but probably just looking at the names, you kind of guess what they are doing, right? You see there's a huge number of even specialized types. These are all W3C standards, these types. Durations, date and times, and so on. Okay. Now, do you remember that yesterday I told you that even when a document is not really structured, like for example, there was an array that was heterogeneous. There was a string, there was a Boolean, there was an object. And I told you technically in a schema, you could still say, I want an array of whatever. Well, the way you do that, the whatever is called item in the JSound and JSONic universe. So if you say location item, it will just accept anything. It's basically absolutely anything in there. So here it turns out to be an array of strings, but item just means anything. It's whatever. Okay. So an example of use of item, if you want to say an array of items, this is how it is. It looks very intuitive in the syntax. An array of items basically means an array of whatever. So here that would be valid. It would be valid against this schema because you basically accept anything, any item. Okay? Item is just a generic name. You could also enforce something more specific, like saying, I really want an array of integers. And that would be valid against the schema, right? You can also have an array of objects that have an optional key foo that must be associated with a Boolean. Here, that's the case. All of the objects in there are foo with a Boolean. So this is all valid against here. It's the array of objects. Who is with me? Right? Who sees that it's intuitive? That this really looks very much like the instance here. So technically, you can take an instance and turn it into a schema very easily because it's really just replacing it with this generic layout right here. Okay. I should stop because, yeah, I was seeing that it's going to ring. So I will continue next week. Thank you very much. Enjoy the exercises that the TA team has prepared for you, and I'll see you next Tuesday at 2 p.m. Thank you.